Great. And yeah, so you'll need to go into full screen probably.
Yeah, 1 second.
Great.
So
Perfect.
hopefully that looks all right.
Yep, that looks great. Great. And so Paul will be telling us about the impossibility of Landauer's bound for almost every quantum state. Please take it away.
Great, thank you. And greetings from Singapore. Happy to tell you guys today about my recent work with Milei Gu on the impossibility of Landauer's bound for almost every quantum state. So if I can change slides, yeah, there we go. So I found this work really exciting because it allows us to revisit and revise our understanding of the relationship between energy and information. In the process, we gain a deeper understanding of both physics and computation. So this relationship between energy and information has been investigated for a long time via thermodynamics. So a natural question along these lines would be, what are the thermodynamic limits of computation? Actually, take a second to think about what you would answer to this. We have a lot of experts in the field here. So regardless of your background, probably Landauer's bound at least comes to mind. And this is the idea that to reset memory requires heat flow to the environment. And more generally, to compress state space for a logically irreversible transformation requires heat. So here, to start setting up some notation, the expected heat Q must be larger than the reduction of entropy, S, times the thermal energy of the environment, KT. And so, for example, when we're resetting either a bit or a qubit from the fully mixed state to a pure state, we get the well-known KT log 2 result. So now you might think, well, quantum computation should be able to avoid this actually, because that's just unitary gates. So basically logically reversible. But it's important to keep in mind, actually, there's a lot of non-unitary operations needed for quantum state manipulation and quantum computation also. So just some examples, if you're trying to initiate or reset your quantum memory register, if you're preparing a Bell state in a lab, or really any special state from whatever the pre-existing state was, hopefully one day when we have quantum error correction, all of these are examples of non-unitary transformations, which are then subject to Landauer's bound and heat requirement. So basically, Landauer's bound is this accepted exchange rate between energy and information. And from a modern perspective, it essentially restates the second law of thermodynamics, that entropy production is expected to be non-negative. Here, I'm using sigma to denote entropy production. And from this perspective, we see that entropy production can only go to 0 in this quasi-static limit where you have full control. And so Landauer's bound also will kind of only be met in that limiting paradigm. So maybe a better question is, what are the non-equilibrium thermodynamic limits of realistic computation? So here by non-equilibrium, I mean finite time control. And by realistic, I mean some kind of constraints on knowledge and control. So Landauer's bound is out. Are there stronger constraints that we can put on entropy production? Well, indeed. And the main result that I hope to share with you today is that no reliable protocol for preparing a quantum state can achieve Landauer's bound for any more than at best one of infinitely many possible inputs to the preparation device. So in particular, we find that for any preparation device, there's going to be a unique minimally dissipative input. We'll call it alpha naught. And for any other input to this device, the required heat is larger than Landauer's bound by something proportional to the quantum relative entropy between the actual input and this minimally dissipative input. So at this point, it's actually useful just to look at the mathematical, to think of the mathematical properties of the quantum relative entropy, because this immediately tells us about some of the physical implications. In particular, if this minimally dissipative state was getting close to a pure state, or really any state with limited support, then for generic input, the heat will be diverging. The lower bound on the heat will be diverging. So this isn't only a new bound, but a quite severe bound on heat requirement that we should really be paying attention to. So it's worth asking, well, what goes into this derivation? And really, there's not too many assumptions. We use a really general quantum dynamics, where the total Hamiltonian of system Bath's supersystem is controllable, or at least partially controllable. There's a control parameter x at each time, which denotes all these control parameters. And the protocol goes from time 0 to tau. That Hamiltonian induces a net unitary time evolution of the supersystem. And of course, you take your partial traces to get the system at any time of system and environment. Now we want to go from dynamics to thermodynamics. And in non-equilibrium thermodynamics, the main object of interest is entropy production, again denoted by sigma here. So entropy production is the entropy flow to the environment beyond any compensating reduction in the von Neumann entropy of the system. And you can keep in mind that entropy flow is things like heat going to some part of the environment divided by the temperature at that part of the environment. Now, without making any further assumptions, we get not only a bound on entropy production, but an equality. And we find that entropy production is exactly quantified by the change in mutual information between system and environment, plus the change in relative entropy between the environment and a reference state that would represent the environment in local equilibrium. So a kind of curious and fascinating thing about this is that it doesn't require the non-negativity of entropy production. In fact, you can expect entropy production to be negative for some processes. But to recover the second law of thermodynamics, we can impose two further restrictions. So for example, if we assume that the system and environment are initially uncorrelated and that the environment begins in local equilibrium, then indeed we recover the second law. And by the definition of entropy production here, this immediately implies a very general form of Landauer's bound, that the entropy flow must be larger than the reduction in von Neumann entropy of the system. And also what this sort of derivation of Landauer's bound tells us is that any non-zero quantification of entropy production gives a sharper bound than Landauer's on the heat requirement. So keep that in mind. So now we want to talk about the thermodynamics of any quantum operation. And there's many ways to implement any particular quantum operation gamma. But if we fix the initial state of the environment and we fix the control protocol, then that gives us a fixed implementation for that CPTP map gamma. Now we want to ask, for a fixed implementation, how does dissipation depend on the initial state of the system? So I'm adding this subscript rho naught here to emphasize this initial state dependence. And what we find is that there's, for any minimally dissipative state to this, for any minimally dissipative input to this operation, there will in general be some amount of entropy production. But for any other input, there will be even more entropy production, which is exactly equal to the contraction of the relative entropy between the actual input and that minimally dissipative input. And if we think of the quantum relative entropy as a measure of distinguishability, we see that this is dissipation from the loss of distinguishability among quantum states. And the implications are really profound from this kind of neat result. Foremost, we find that non-unitary operations cannot be thermodynamically optimized for all initial states simultaneously. So recall things like initiating a qubit register, creating a Bell state in the lab, quantum error correction, all of these non-unitary processes which have a non-trivial Landauer's bound also cannot saturate that bound for all inputs to the device, no matter how you build it. And so it's interesting to compare this to the classical result obtained earlier by Kolchinsky and Wolpert in terms of the Kullback-Leibler divergence. And we find that the quantum correction is exactly the change in coherence on the minimally dissipative eigenbasis. And we find immediate implications for the thermodynamics of quantum computing. So first, we find that there's a thermodynamic penalty for modular circuit architectures, which is due to a loss of correlation among the modules. And with the rest of the time that I have today, I'd like to talk about the divergent thermodynamic cost during quantum state preparation. So the goal here is to reset all initial states to some desired state, R tau. And we'll say that the implementation is reliable if it takes the final state within epsilon distance of the desired final state for all inputs. And as you might imagine, if we're taking all states to basically the same final state, that final relative entropy goes to 0. And the result I showed you earlier simplifies to say that for any reliable reset protocol, there might be some minimal amount of dissipation for a special input, but for all other inputs, there's even an excess entropy production proportional to the initial distinguishability between the actual and minimally dissipative inputs. And we can recover the promised bound in terms of heat that I showed you earlier if we just assume that there's a single thermal bath at temperature T, and we'll also assume the second law of thermodynamics. So here we have this, I'd say, elegant, maybe even cute theoretical result. But I think it'd be fair to ask, well, okay, what is it good for? Because at this point, it might seem that alpha naught is still some kind of abstract quantum state in this vast Hilbert space. So, how do we find alpha naught? That would make this result much more concrete and actionable. So that's what I want to show you next. And so now it's important to recognize that the entropy flow is an affine function of the initial state. And here I'll just talk about qubit reset for simplicity. And so we find that we can define this thing we call the entropy flow vector. And the entropy flow from any initial state is going to be expressed simply just in terms of the entropy flow from the fully mixed state and something to do with this entropy flow vector. And A here is just the block vector for the input state. Okay, so now let's say that in your lab, you have some preparation device to prepare a quantum state. Okay, now take any 4 initial states that you have access to. For example, this might be the X, Y, Z, and minus Z states. So you put those through your preparation device and you observe the amount of heat or the entropy flow produced from those 4 initial states. From that, there's a simple linear algebraic transformation from which you can get these 2 objects of interest. And then we find analytically what the minimally dissipative state is. So here, A star is the block vector for this minimally dissipative state. And we see that it's just this simple algebraic function of the entropy flow vector. Now, let me give a quick example. And in this example, we'll assume Lindbladian dynamics. We'll assume that we can control the energy gap and the orientation of the energy eigenstates. And by doing this, we want to, of course, reliably reset to some state 0. So here's our first example of reliable reset. And in this example, what I'm doing is I'm just sigmoidally increasing the energy gap, and I'm rotating also the energy eigenbasis. The top 3 panels on the left shows the time evolution of the block vector components for 10 random initial conditions. The bottom 3 panels are just showing the evolution of thermodynamic quantities. We can see here that this is indeed reliably resetting the state. And on the right, now we'll see we're comparing entropy production to the relative entropy for 1,000 random initial conditions. And the red circles along the diagonal are strongly validating our theoretical predictions, where and also these blue crosses, the horizontal offset is showing the importance of coherence in each of these cases. So one thing I'd like to point out to you here is that here in the block vector, we show with the star, we show the minimally dissipative state for this protocol. And I'd really like to emphasize that the minimally dissipative state can have, as it does in this case, can have coherence in the energy eigenbasis. So it can actually be thermodynamically favorable to have coherence in the energy eigenbasis. And we also see that this state is something close to a fully mixed state. And also that the coherence relative to that minimally dissipative state always leads to dissipation. So here's just one more example. It's the same type of dynamics, but a different control protocol. In this case, we're just considering a fixed large energy gap, and we're letting the system relax to equilibrium. And now in this case, you can see the minimally dissipative state is close to a pure state. So because of that, the dissipation from most states must be very large. And we see indeed this is at least an order of magnitude larger than Landauer's required heat for most inputs for this specific example. Again, it's strong validation of our theoretical predictions, but it emphasizes that that sensitivity to the pureness of the minimally dissipative input. And we also see that the coherence doesn't really matter that much for this example, because the relative entropy of coherence is strongly bounded by the dimensionality of the system. So if dissipation is large, then the classical result explains basically almost all of the dissipation. Okay, so there's at least two reasons to really care about the results here. The first is just energy efficiency. So you want your battery to last as long as possible on a single charge. The other reason is maybe even more important for getting quantum computation off the ground in the first place. And that's basically that if you have local on-chip heating, if we extrapolate out, we have so many qubits on the chip and all these transformations. If there was a lot of heating, you would imagine you would have noise and decoherence, which is going to mess up the whole endeavor, where we really need these delicate sorts of superpositions. So it gives good reasons to pay attention to the lessons learned, which, just to reemphasize, we found that non-unitary operations cannot be simultaneously thermodynamically optimal for all inputs. So this suggests designing your device for the expected input. At the same time, we find that there's a thermodynamic penalty for misaligned expectations. In particular, dissipation diverges for generic inputs to preparation devices as that minimally dissipative state approaches a pure state. So with that, I'd just like to point you guys to these two papers that the talk was based on. And if there's time, I'd love to take your questions. So thanks.
Thank you very much. Another interesting talk. So yeah, if there's any questions, please pop them in the chat now. Otherwise, this I guess brings this part of the session to the end. And I don't know if I should pass back over to somebody else now to say what the next plan is. But as always, if there's no questions coming through, just to reiterate that there's still the Slack. So please, we do have a question coming in. Maybe we should just take one question from Gabriel Landi, who asks, do you have any idea what happens when the temperature goes towards absolute zero?
Hey, Gabriel. Well, gosh, it's a good question. I think maybe you have a paper on this. So it's interesting in that as temperature goes to zero, that KT log 2 or whatever it is less meaningful, just because temperature is small. So I haven't thought about it a lot, but maybe be interesting to try to reach a sort of hybrid result on this. Yeah, there's some, let's see if I can get here. There's some kind of interesting situation though, when if you're trying to reset a state using a very cold bath. So this is somewhat relevant. let's just say your bath states are almost pure, and you're just going to swap with one of those to get to reset your system. Then the entropy production turns out to be the relative entropy between the initial state and something that's almost pure. So actually, the entropy production is basically diverging here because you're totally messing up your bath, which was so close to pure. So I think in terms of heat itself, it might not matter, but in terms of entropy production, it matters a lot because it's going to take a lot of effort to repurify your bath. So hopefully that's something useful to keep in mind.
Maybe we can just take one final question from Gonzalo, which is, he asks how crucial the assumption that the CPTP map is fixed. And he says, do you have any idea on how your results may change if you allow some information about the initial state to be erased?
I get the first part of the question, so I'll answer that, and then I might need a reminder about the second part. So for the first part, let's see here. So for the first part, you were asking about a fixed implementation. And basically, to be able to talk about the initial state dependence, the way we framed the problem, that question only even makes sense if we have a fixed implementation. So if you have some correlation, then you're not really able to choose that initial state independently. So I guess this result here that we have first allows for arbitrary initial correlation. But then the next result that we have in terms of this initial state dependence, it assumes that you're just popping in to your circuit some rho naught that's uncorrelated. And so that's basically for some fixed implementation. So there are generalizations of this result that I've found when you go to more general scenarios, but I'm really not sure how useful they are, but I'd be happy to talk about it.